Evening, ladies and gentlemen. Thank you very much for giving me voice. Today I will be talking about ethanol production, this way of recent publishing processes, article by Lisboa Technical University written under leadership of Professor Francisco Guerrio. The untitled work was Sustainability Assessment of 2G bioethanol production, residual lignocellulosic biomass. The development of sustainable biofuels can help to reduce the reliance on fossil fuels and mitigate the impact of climate change. The study analyzes bioethanol production from agroforestry, residual biomass, namely eucalyptus residues, and corn starter. This study includes process simulation using Aspen software and life cycle assessment. The economic analysis on the biorefinery economic viability, equipment, and production costs reveals a positive decision for from residuals and eucalyptus and transportation costs. Removed ethanol selling price obtained was 2.19 euros per liter, and for eucalyptus residues and stone starter. Globally, global energy consumption has risen mainly due to population growth, technological progress, and economic development, stimulating greater use of non-renewable sources. This amplified demand has mainly focused on fossil fuels, significantly contributing to the acceleration of global warming. In 2022, direct primary energy consumption from natural gas, oil, and coal was from 39 to 45 watt hours, with 58 in the United States and China together. As a result, this caused several consequences, including climate change, environmental degradation, and harmful consequences on human health and biodiversity. Given these environmental concerns, biofuels have emerged as a promising alternative to reduce the negative effects of fossil fuel consumption, mitigate greenhouse gas emissions, and reduce reliance on non-renewable energy sources. Biofuels are a category of bio-based fuels derived from biomass capable of serving as substitutes or additives to conventional fossil fuels such as gasoline and diesel. Between 2023 and 2028, biofuel demand is projected to surge by 38 liters, an increase from the previous 5 years. By 2028, overall demand is expected to reach 200 billion liters of renewable diesel and ethanol driving two-thirds of this growth. Emerging economies such as Brazil, Indonesia, and India lead in demand, propelled by robust biofuel policies and rising transport fuel needs. The European Union's United States focus on transport policy enhancement with renewable diesel and biojet fuel as growth segments like electric vehicles. Biomass derived from organic matter found in animal and plants serves as valuable resources for energy and biofuel production. It includes a wide range of sources. Lignocellulosic biomass consists of three primary components: cellulose, hemicellulose, and lignin. Cellulose, comprising 40 to 60% of biomass, is a crystalline rigid polymer of glucose monomers linked by 1.4 linkage, making it resistant to enzymatic degradation. Common hemicellulose, constituting 20 to 40% of biomass, is an amorphous branch polymer of pentoses and hexoses, making it hydrolysable due to its less structured nature. Lignin, accounting for 10 to 25%, is phenylpropanoid polymer providing structural strength and resistance to degradation, and its phenolic byproducts can inhibit enzymatic action. Forest in mainland Portugal is primarily comprised of species like cork oak and maritime pine, making up about 69.4% territory. Thus, annual production of forest-based residual biomass reaches around 3 billion tons. The agriculture uh, residual biomass, which straw from farming and agri-food industry byproducts, comprises materials such as cereal straw, olive tree cutting, olive pruning, and pomace. In mainland Portugal, the focus is corn cultivation, predominantly located in central regions. Corn cultivation produces abundant residues of straw rich in cellulose and hemicellulose, making them ideal for biofuel or bioproducts production. Biofuels are commonly classified into the first and second generations based on their feedstocks. First generation biofuels are derived from food crops or edible feedstocks like sugarcane, corn, wheat, and vegetable oils. While they are completely widely implemented using food crops for biofuel productions, raises concern about potential impacts on food security and competition with food production. Second generation biofuels are produced from the non-straw feedstock, including agricultural residues, corn starter with straw, dedicated energy crops, non-edible parts of plants, and from eutrophic microalgae. In general, these biofuels are produced using more advanced technologies and aim to avoid the competition between fuel and food. Bioethanol is a renewable fuel derived from the fermentation of biomass sugars into ethanol. Commonly blended with gasoline, these blends can range from low level from Example up to 10% or to high level and like 85 ethanol and 15 gasoline. Ethanol enhances fuel oxygen content with 35% of oxygen in combustion, reducing greenhouse gas emissions and promoting cleaner combustion. Ethanol has a high octane number, indicating the resistance or to engine knocking and early emission. This contributes to improved engine performance and efficiency. Biorefineries are commercial and emerging plants that process bio-based feedstock into biofuels, biochemicals, and bioenergy. They significantly contribute to sustainability and the growth of clean energy economies through the emphasis on high waste energy efficiency and zero production waste. However, 2G biorefineries are still in development due to advanced technology and complex process integration required. Technology development aims to enhance efficiency and scalability by updating processes. Currently, given the commitment to reduce dependence on fossil fuels and to reduce greenhouse gas emissions, some countries have adopted policy measures to encourage renewable fuels. Several techno-economic and life cycle assessments of 2G biorefineries have been performed in the past decades for different types of feedstock and geographic location, such as spruce log residues in Sweden, palm empty fruit branches, or integrated sugarcane-based biorefineries. In Brazil, bioethanol production from corn crop in different locations, corn stover in Mexico and Belgium. This study involves the simulation of 2G bioethanol production in Portugal using two different residues through a four-stage biochemical route: biomass pretreatment, enzymatic hydrolysis, fermentation, ethanol recovery. Subsequently, after implementing the process model, a comprehensive economic analysis was conducted to evaluate the economic viability of 2G bioethanol production using the feedstock. Additionally, life cycle assessment of the bioethanol production was carried out to estimate and evaluate environmental impact. The process simulation was carried out using the Aspen Plus software, applying the thermodynamic random to liquids models. The physical and thermodynamic properties of biomass and raw materials for the process were obtained from the National Renewable Energy Laboratory. The initial composition of eucalyptus residues and corn stover for samples that provided by the private company Florecia is shown. Glucan and xylan uh, are used as are considered solid, defined acetyl groups. The extractives were defined as constituent mixed. The process simulation was carried out using the Aspen Plus software. The physical and thermodynamic economic properties for these processes was obtained from to 15% glucan. The biorefineries produced with 100,000 tons of dry biomass annually for 330 days operational days to 7,920 on semi-continuous schedule. The process was then divided into sections: milling, steam generation for pretreatment, enzymatic hydrolysis, fermentation, and bioethanol distillation and purification. The steam generation and pretreatment going is finally an expansion tank. In the second tank is hydrolysis. This by expansion tank is going to by hydrolysis to fermentation and then finally to bioethanol recovery. The first step in bioethanol production from lignocellulose biomass involves milling the feedstock to reduce the particle size to circa 20 milliliters to enhance its accessibility for subsequent processing. The simulation on aspect class was performed using crusher equipment. Steam explosion, a variant of hydrothermal physical-chemical technology, was chosen for the treatment of lignocellulosic biomass since it is recognized as one of the most cost-effective processes for hardwoods and agriculture residues, being used in several demonstration units in the first commercial 2G ethanol unit. Steam explosion involves exposing the biomass to high-pressure steam at high temperature, typically at between 160 to 260 degrees, corresponding to followed by rapid pressure release to atmospheric pressure. When biomass is subjected to high pressure and temperature, it undergoes chemical reactions that break the chemical bonds between cellulose, hemicellulose, and lignin molecules. In order to stimulate the process, aspen were stimulated by yield tractors. Stress treatment methods employs high pressure and high boil steam to treat biomass. Steam is generated by burning natural gas in a boiler, which heats water to its targeted pressure of 7.5 bar, resulting in steam production. These studies separate hydrolysis and fermentation. Configuration was employed involving pre-liquefaction of biomass. Enzymatic hydrolysis was conducted at 50 degrees and 1 bar. Based on the previous know-how, the team, in order to enhance enzymatic hydrolysis efficiency, the treatmented biomass was subjected to pre-liquefaction in a rotating drum for 1 hour. The eucalyptus sawdust treatment was by steam explosion. The fermentation took place at 30 degrees with inoculation of 5 grams per liter of Sargodha case scenarios. Aspen class fermentation stage was simulated using a reactor mixer introduced to inoculum and a heater to cool the hydrolysis to 30 degrees. The fermentation gases such as carbon dioxide was released the stimulation of separator equipment. Distillation is one of the techniques used to separate ethanol from other solutions such as fermentation broth, giving the ethanol wastewater isotope distillation is based on the difference in volatiles at pressure and the boiling points of ethanol at 78.2 degrees Celsius. The purification of ethanol is achieved through pressure swing adsorption and process that uses adsorbent steroids to dehydrate ethanol. This method enables ethanol to be purified to a concentration of 99%. Ethanol purification is simulated by a set of separator equipment. After purification, the ethanol is subjected to a heat exchanger to decrease the temperature from 116 degrees to 80 degrees at 1 bar. Methodology of heat integration. Heat integration is extended to reduce energy consumption by strategically combining processes that require heat, steam, or electricity, enabling the practice of responsible and efficient results management. The analysis of the heat transfer equipment and the utilities employed in the process illustrates an effective strategy of utilizing available energy from exothermic reactions to meet the heat requirements of other processes. Enzymatic hydrolysis and fermentation involve exothermic reaction that occurs 50 degrees Celsius and 30 degrees Celsius respectively, releasing available energy. This available energy resource, regardless of specific reactions, can be redirected to other processes requiring additional heat, such as biomass pretreatment. The biomass pretreatment involves high temperatures and requires a high amount of utility, with the biomass heated from 100 Celsius to 206 for this stage. The economic analysis considers parameters such as capital expenditures, operational expenditure, production costs, and net present value at minimum ethanol selling price. The CapEx includes process equipment and all components needed for the operation, such as piping, instrumentation and control, electrical systems, land and buildings, and also indirect costs related to the project supervision, construction, and contingency. The analysis assumes a 20-year project lifetime and an initial total investment of 3 years, an annual interest rate of 2%. The net present value calculation is a specific rate for energy industries calculated by the weighted average cost of capital with a value of 6%. Life cycle assessment is a method for assessing environmental impacts by systematic analyzing industrial and products in terms of the energy and material inputs as well as the residues and emissions. According to the international organization, the standardization, this tool is divided into 4 goal steps: goal and scope definition, life cycle analysis, life cycle assessment, and results interpretation. Life cycle analysis was conducted in CIMA-Pro utilizing a Covinvent database. The first step in life cycle assessment is to the current scope of the study, which should clearly state the intended application and specify the system being studied. The life cycle inventory analysis comprehensive of the flows within the defined system boundaries. The life cycle impact assessment involves four main stages: classification, characterization, normalization, and weighting. The, the mass and balances software for eucalyptus residues and cornstalk. Eucalyptus residues and cornstalk was biomass 4.85, molasses was 1.8, and cornstalk 5.5. In the eucalyptus residue scenarios, 1.41 tons per hour of bioethanol was produced from 1262 tons of hours of dry biomass, resulting in a total yield of 0.11 ton of bioethanol per ton of dry mass. The yield scenario corresponds of bioethanol per ton of dry biomass considering a density of 734 kilograms per square meters. For Constable, 131 tons per hour of bioethanol was produced, with yield of 0 to 1 to 147. The utilities consumption is primarily attributed to the initial biomass treatment stage, the final bioethanol purification, and reaction. The characterization results of acceleration are also eucalyptus, which is in the forest of Portugal. This is the pest kind that will be eliminated because it destroys the national countryside, national European trees. So this is using of eucalyptus very widely. So acidification, eutrophication, and these were centers to scenario high environment factors over the compared to stone cover. This is a climate change category for eucalyptus residues in an impact, while the ethanol production from cover stone results in 0.2554 ethanol. The life cycle analysis, the weighting results involve multiplying the obtained results by weighting factors that express relative importance to each category. There's additionally four alternative scenarios were examined to assess environmental impacts related to identified hotspot enzymes, production in situ scenario, heat integration, and scenario renewable energy scenario, renewable energy and enzyme production scenario. They illustrate the climate change category for the scenario. Enzyme production results in 48% reduction in carbon dioxide equivalent emission for eucalyptus residues, reduction for the cost of a ratio. This is 89% equivalent emission for feedstock biomass. The ozone depletion impact is resulting in 92% in reduction of emissions with using enzyme production. The was waiting for an alternative scenario. The base scenario, the enzyme production scenario, has most impact reduction with 64% residues of eucalyptus and 58 of cornstalk. So enzymatic would be the base higher than the thermal. This study aimed to analyze the standalone advanced bioethanol production using eucalyptus residues and cornstalk as feedstock. This study had some process simulation, equipment design, and liquid life cycle analysis to compare economic cost of bioethanol production according to the temperature can vary between 0.22 and 1.11. However, the scope is processes, thereby potentially reducing product costs. In the current tunnel selling prices, molasses sales involve the direct sale of byproducts, while enzyme production expenses were not considered. All these scenarios were common future. So this is what I wanted to say for today. Thank you very much for listening to me.